Swayam Prabha. Digital India. Educated India.
So in the last class, we have seen concept of how do you get going about selection of actuators and sensors for a mechatronic system, and now we'll just get more familiarity developed into the concept of feedback. The sensors that we used in mechatronic systems are mainly for feedback. Now, how do we process this feedback or sensor input to further drive the control application or to get a desired kind of application going? That is what we are going to see now in the next part of the course. Although this might be somewhat familiar to you, you have already, some of you might have already seen the feedback in the context of your Mac course or any other automatic control fundamental course. It's important to get a firm grip on this concept of feedback, so as to kind of use it in the case of the systems that we have not yet been exposed to. For example, these nonlinear systems or Lagrange formulation based systems, or any even linear systems, but added with the nonlinearity of the friction or backlash. So in such cases, how do you think about using the tools that you have learned already? Say for example, Laplace transform, if you say, they will not be applicable because they are valid only for the linear systems case. So then how do you go about doing such a analysis? So that's where you need this fundamental understanding of this concept of feedback, so that you can apply it with the tool of this ordinary differential equation to many different kind of systems. I mean, maybe it will nonlinear or linear or nonlinear, and get to know what is a way you can think about in the case you are not given that the system is linear, and the tools in the linear domain what you have learned are probably not applicable. So let's develop this understanding further now. If you see, what we are going to see is basically the what is feedback, how do you what is called as feedback, and open loop versus closed loop kind of systems. Okay, you may feel this is like a trivial thing, but nonetheless you should go through some part of it, or make sure that all the parts of these are understood, so that you can apply them in the cases of nonlinear systems as well. So how do you process the feedback variable to achieve desired goal? That is another kind of a very more like a design question. Okay, so there are many different ways in which one can process feedback variable to achieve what goal that is given to you. Some part we have already some kind of a feel based on our intuition or based on our common sense, so to say. We know how do you process this variable, but how do you convert that understanding into some sense of mathematics and use it further? This is another question that we need to bother about. As we go along, we'll start slowly unfolding answers to these kind of questions. Okay, so now let's take an example, but before that we need to be sure about given a plant, what are the inputs and outputs. You should be very sure about, okay, oh, this is my input or this is my output. based on input and output, like the kind of development of control and its properties may have a lot of changes that will happen. And then establish relationship between input and output, which is what we saw. I mean, mathematical modeling will give you that. And once we have that relationship and we know these inputs and outputs, we are kind of more or less ready to kind of delve into this development of control algorithms. Okay, and there are several representations that can be possible for system, but right now we are going to look at mainly this ordinary differential equations kind of a representation, which is the most fundamental form for the representation. Okay, the state space transfer function, they are valid only for the linear systems case. For nonlinear systems, you may have a state representation of a system that we'll consider later for control development in a different way. But ordinary differential equations are the most fundamental form of representation that one can use for analysis of or propose any control and then do the analysis or synthesize the control based on the equations. Okay, how do we do that? We'll see soon. Okay, so let's take this example of a block lying on the, this is our standard example, this block with mass m on the surface, horizontal surface, and it is currently at this position, and now this F is applied on the block. Okay, so let's assume for now that there is no friction between the block and the surface, and under such scenario we want to drive this block to the desired position shown. Okay, so what is the quantity of interest here? Quantity of interest is x, okay, the desired position. So position is a quantity of our interest. Okay, so x is a quantity of our interest, which is output, and quantity that you can dictate, okay, is input to the system is like force F. So force F is can be any value that we want to apply. Of course, I mean, when we talk of mechatronic system, this F will have some certain saturation limit, but right now theoretical discussion we consider, okay, whatever value of F is desired, okay, you are able to apply. Okay, so this F is something that we want to dictate in such a way that we reach the final desired position. So we see first the relationship between input and output, which is standard F is equal to mx double dot. And now under such a relationship, if we want to kind of pose this question, okay, to take the mass to the desired position xt, what should be the applied F? So there are many solutions to this problem. Okay, one simple way, if you remember, we had done some kind of a planning for the trajectory. If you recall, the trapezoidal plan for the trajectory, that okay, I'll start moving the block along some kind of a trapezoidal trajectory, such that the final point of the trajectory is taking me to this desired position. Mind this desired trajectory, trapezoidal trajectory, is in the voltage. I mean, it's in the velocity. It's not voltage. It's in the velocity x dot. Okay, so you plan x dot along the trapezoid such that you accelerate first, you move with a constant velocity, and then you decelerate, and you are reached in the final desired position with the velocity in the final position 0. And we also begin with 0 velocity in the starting position. Okay, so if we plan such a trajectory, we get some x desired dot first, and then we get if you differentiate that, you will get x desired double dot. So if you see along the trapezoidal trajectory, these are just a pulse of acceleration. So you see, trapezoidal trajectory velocity means if you take a derivative of this, then initially the velocity, the derivative will be positive, is a positive slope of the trapezoid, and then for some time duration, whatever the time duration, then you apply 0 x double dot, and then you apply like x double dot, which is reverse. Okay, so that's how the trapezoidal trajectory will define the desired acceleration. Now if we know this desired acceleration xd double dot, okay, which now will be in terms of these pulses which are coming. So these two pulses, okay, one is for the beginning of the trapezoidal trajectory, and which is positive pulse, positive x double dot, and then at the end of the thing it is like a negative x double dot. Okay, so these two pulses are to be applied as f, like they will be scaled by mass m, and if we apply these pulses, we hope that with these the desired position would be reached. Okay, so this is one of the many kind of trajectories of f that can take you to the final desired position. Okay, so this particular way of doing things, where you are really not using any information about where I am at the moment, okay, along the track. If there is no dependence of f at all on x, it's directly function of x desired, and x desired is what is I have planned. Okay, so this is important to know that, okay, this f has no any kind of dependencies on x explicitly. Okay, so under such scenario, this f will be an open loop control. So can you see what is the problem with such a solution, where you have just an open loop, some kind of a force that is applied here. I'm not looking at what is my current x position, and I'm still keeping on applying whatever f I have computed based on the knowledge of the system, and I'm hoping that I'll be taken to the final position. Okay, so this is some kind of an open loop based control, and we can immediately see that in the presence of friction or in the presence of some other disturbances that are there around here, we may not be reaching the final position. Okay, so that is a issue with this kind of a solution that we have developed. Okay, so now then the question comes that look here, I mean, I've mentioned the same thing, no feedback. So we have not used the feedback of our input output variable x here. Okay, so we would not know if we have really achieved the task. Okay, so we have given this input trajectory and forgotten about it, and then now if we look, okay, oh, we find we are not at a desired position. Okay, so then, like, no, we'll have to do something. Okay, so we are not really looking at whether we have achieved the final goal or not in real time. So we need some sense of current position, and make use of the same, develop this f to be applied. So mathematically this question can be posed. Okay, say for example, if you are given this kind of a scenario with your eyes open, and you are saying, okay, oh, I want to, you apply force whatever you want to this block, or your mobile, for example, mobile, to take it from one position to other position. What you would think of doing? See what force you will apply. You will see, okay, oh, I have applied some force, the mass has moved, and, like, I keep on kind of monitoring, okay, oh, has it reached the final position, has it reached the final position? If not, I apply a little more force. If I apply a little more force and it has overshooted the final desired position, I'll apply opposite force to bring it back. Okay, can you see this kind of a common sense kind of a way things will be happening inside your head to get it to the final desired position. So the question is, how do you now convert this whatever you are thinking to get it to the final desired position inside your brain to give it some kind of a mathematical form? Okay, so this is what is the whole synthesis of control algorithm is all about this question. Okay, so you feel okay, oh look, if I like look at this position, or if I am monitoring this desired monitoring this current position, how far is away from my desired position. I do apply some things input such that you know I would go to the final desired position in some way. So if you see what exactly would do, suppose somebody asks you, okay, look, there is a competition, and the person who takes this block from current position to the desired position, the fastest possible way would get gold medal. Okay, so this competition is there. So now you are thinking now, like, okay, suppose I do like, no, so initially if the error is high, I would apply like large force. But if I apply large force, I go fast, but then I have a danger of overshooting this. So I need to apply like, you know, some kind of a force which is again reduced as I come closer and closer. So this is kind of a thinking that you would carry out in your mind. Okay, or in some place I may have to accelerate first, and before I reach desired position I need to start decelerating so that I can control myself to kind of make sure that I don't overshoot. Okay, this kind of a things may be happening in your mind about when you're participating in such a kind of competition. So the question is, how do we convert this this whatever knowledge that we develop as a commonsensical thing into some kind of a mathematical form? So the question is like, what is a function f of like, some function which is a function of x, such that, okay, so this is not a function of time explicitly, it is an implicit function of time through x. Okay, so f should be what kind of a function of x such that we achieve the desired goal. Okay, so pause here and like, propose some function. Okay, and then like, we will try to kind of see what we can do with that kind of a function. Okay, so this function should be involving x in some way. So the simplest kind of a solution one can come up with, okay, is make sure, like, see that error, as I said, like, error between current x and xd, and make f to be some function of this error. So we want f to be 0 when error is 0. So once you go to the final position, we don't want to apply any force. Okay, you will agree with me on that, right? You don't want to apply any force once I'm at the final position. But now if I just do this, okay, that apply f proportional to this error, okay, error between current position and final desired position, then what would happen? Okay, think about that. Okay, will I really reach the desired position, and then f will be 0 there? Although f is 0, will I stay there forever? Okay, those kind of questions that we need to ponder over. Okay, that's one way of thinking. Other way of thinking is to see, like, if I put in some kind of a virtual system of springs and dampers, such that the equilibrium position for such a spring and damper is my final desired position. Okay, so this is another kind of a maybe philosophical or maybe conceptual thinking that one can do. Okay, so you say, okay, well, if I put some kind of a damper, and this is like a more kind of physical way of looking at things, that I throw in some springs and dampers in a virtual way, like they are not there in a practical system, but I am thinking of putting them as a virtual kind of a elements in the system which will finally drive my system to my desired goal. Okay, so these are the two ways one can think about, and in either way, like one has to kind of do the analysis to make sure that we verify or validate that whatever we are proposing is indeed doing the job that we would like finally to happen. Okay, that is this our goal: place a mass at the desired position. Okay, so here again this is like a regulation problem. If we have discussed the regulation problem, and we are not interested in path along which this mass moves. Okay, although straight line in time it can be different paths. So but we are kind of interested only in like reaching the final position. So let's propose something. Okay, um, say we propose some function, then we need to know how this f would work towards getting your goal achieved. So let's propose this. So this f that is proposed here, okay, this is some kind of a error multiplied by some proportionality constant, okay, which you may be familiar with in a proportional kind of a control action that is happening. So kp times e is giving you the final form of f proposed, okay, and which when you use this, how do you validate that okay this will work or not work? If you put this expression into this equation of dynamics, okay, that is going to give us what is going to happen. Okay, so I put this f into the equation of dynamics, and we find the equations which govern the error dynamics. Okay, so this is a very important step, that okay you find what is the equation that is governing the error dynamics once you propose some value for some function for f. Okay, some function for control input if it is given, then what is the final error equation that you'll get is very important to kind of get to this equation. Now by observing this equation, we can see here this is a harmonic system. Okay, so the error, there is no damping in this system. So initial error, suppose it is E0. Okay, the final error will keep on oscillating between the values E0 to minus E0. Okay, so the error will oscillate. That means like your mass is going to kind of oscillate around this desired position continuously. Can you see that with this equation that is happening? And once I apply this kind of a force, like although the force gets zero at desired position, the inertia built in the system is such a way that it is kind of pushing my system, that the velocity is not yet zero here, so my system is getting pushed on the other side, and again it will come back, again it will go back, on the other side it will come back, like that it is keep on oscillating around the desired position. Okay, so how do you take care of these? Okay, so now you can observe this equation and see, okay, what we want this equation, desired form for this equation to be. Okay, so we need some kind of a additional element which is a damping here. So we put that additional element in this desired form. So this is my desired form I would like to have. Then if I would like to have this kind of a desired form, what is a control input which will give me this form, or what is my f which will give me this form eventually. Okay, so this is how one has to think about in the space of ordinary differential equations to analyze systems. So I am taking this very simple example to not get a concept across. This can be extended to whatever complicated dynamics that you are looking at. Okay, see, this is a pure kind of a differential equation kind of a form of analysis. So even if you don't know what are zeros, poles, nothing, no concepts are known, you can just do this kind of a simple analysis to get to the thing. In the presence, especially in the presence of friction and other kind of nonlinearities, if you do this analysis, that will kind of give you much nicer insights into what is going to happen than your Laplace transform or the other linear forms of analysis that you might be aware about. Okay, so we can use those forms also. It's not a big, it's not that okay we have to use this. No, what I'm saying is like we should be aware that whenever those forms are failing or they are uh, unable to give you enough information, especially in the presence of nonlinearities, we need to have some backup tools available to us to do carry out this analysis. Okay, so now yeah, you can think about this expression for f is not much difficult to think about. It's just a simple mathematics. If you work out and you work it out actually, and then see what is the form for the f that you get, you'll find that okay, it is your like you well-known kind of a PD control that you probably are aware about in your Mac courses. Okay, so this is what is a main concept now. Like now, we'll see some kind of. I'll pose you some of the problems here, and then you can think about those. Do some kind of analysis, and if you have any doubts or questions about that, we'll take up that. Okay, so you can look at this. This is a PD. As I said, this is a PD kind of a control feedback. Now based on the beauty is like once you have this and this error dynamics known, you can play around with these parameters kd kp to kind of see that okay, error response is controlled in a way you desire, and that will help you tune kp and kd so as to get like whatever desired response. So there are so you have as I said, there are other tools that are available. One can use those tools directly, or one can come to this depending upon whatever is easier or applicable. So that's how one can look at this. Okay, so now let's see this other problem. Okay, so this is the same problem of but now like for the rotary kind of dynamics. So you have the motor, so this exactly like your motor, but now this disc is added on the top of that. Okay, and we have the encoder at the back which will give you the feedback theta. Now our quantity of interest, okay, we want to place this disc as a desired angle. Our quantity of interest is theta, and quantity that you can dictate is input is torque. You may want to take voltage also to be voltage as a input as well. Okay, especially when you know now your model of the motor, and you are actually applying this PWM duty, okay, which is average voltage that is given to the motor, okay, from 0 to 100%, okay, that you are giving this voltage to your motor, and that can be considered as input. Okay, so when you consider this as input, then you can take the motor dynamics part also into account and get your entire model ready. Now this model without friction and without motor dynamics will be similar to previous set of equations, but now I would like you to add, that's your work at home, that you would add motor model to these without considering the inductance in the motor, okay, so that your equations are order of equations remain the same, and you can get now how this voltage and theta relationships are coming up. Okay, the dynamic equation involving voltage will be coming, you'll be getting, and then now for such a system you design now what is the feedback control that you would apply, so that you can do this desired goal of taking this mass from position 1 to position 2 finally. Okay, so this is what your standard control problem could be. So now practically when you start doing that, okay, you'll find that there is additionally the friction in the system. Okay, so now the question is, how do you analyze whether in the presence of friction my proposed PD control feedback will work or not? That's where now you'll see that, okay, the tools of this error dynamics analysis, okay, which we saw for basic concept of feedback and fundamental ODE analysis equations, they would come handy to you. Okay, so I suggest that you incorporate some model of friction, simple model of friction. Say to begin with, some simple Coulomb friction model you can put, okay, into your equations. We have seen all the models of friction. So if you put just a Coulomb friction model, what would be like result of that? So in the presence of friction, can you work out whether my final error will be really zero or not? Okay, you'll find that there will be some kind of a steady state error. You'll not be able to compensate. So that steady state error will be there in the presence of PD control, and that steady state error value will be some function of your gain and friction value. Okay, so find out what that function is. Okay, what the steady state error is. And once you know that, okay, oh, I am like, no, this particular control, so this is what is going to happen in practical case also scenario. So you start commanding your motor to the final desired position, but motor will not go to that position because of the friction. So you can say, oh, this based on the expression of the error, one can get some kind of idea that, okay, if I tighten my gains further, I may be able to go to the final position. Okay, but that's about it. You will not be able to kind of make that zero. So now you get the error dynamics equation worked out, and think about that, okay, for some other desired error dynamic equations, okay, what should be, to get to that, what should be the modifications in the control algorithm that you are proposing. That you think about, and then see if you apply that, can you compensate for friction in some way, or minimize the bad effects of the friction. So this is how one can start thinking when we so see, for example, if in the presence of friction you'll not be able to find transfer function, then you'll say, okay, oh, what I can do about such a system with Laplace transform and other stuff. So that's where, like, no, you'll get into a little bit of a difficulty thinking into the domain of the transfer functions. So that's where, like, this thinking purely in the ordinary differential equation domain would come very, very handy. So think about that, okay, and slowly we'll build upon these concepts. And then there is other problem that one can think about. See, now the goal is different. Goal is to rotate disk with the desired speed. Okay, for this, now what will be your feedback? What's going to be your model of the motor? If you use angle as a feedback, will that help for this? These are the questions you need to think about, ponder over, and, like, come up with some kind of a design for such a. So this is another different problem. Okay, so our control input is same, say voltage, and desired output now is speed is our desired output. So then, like, what is now this new variable which is desired variable output? What will be the equation which is governing the dynamics? So this dynamics now is in terms of omega, not really in terms of theta. So the order of equations will reduce by 1. Okay, so now with that, can you develop control law which will achieve this goal? Can you propose some law and do the analysis, the error analysis? Now you can think over whether now you will require, now that KD term is required in this case. So one can see, like, that this system in terms of omega is going to be first order system instead of second order system, and then there will be no overshoot for such a system. If there is no overshoot, then probably like this damping may not be required. Typically you need require damping to avoid this overshoot that was happening in the previous case. So like that one can start thinking about doing things and getting to a control which will take us to this final desired speed. And now that I want that to happen in the presence of friction as well. So what should I do? Those are kind of questions that one can ponder over, or like think about and come to the come to some kind of a control expression which will take you to your desired goal. Okay, and you prove that with the error analysis you are indeed going to the final position in the way that you have planned. Okay, so like that you can consider now these different other systems. Okay, couple of one or two examples, and you'll form up this concept in your head. Okay, so I think maybe we'll stop here.